Hi friend, my name is Wafiq Azizah. My number ID is 8241231010 and I'm from class C. I study at Tadwako University majoring in mathematics and natural science education in the physics education study program under the Faculty of Teacher Training and Education. In this video, I'm going to share some material if prepared for our English for professional purpose midterm exam. So, let's get started. Alright, now let's move on to the material if prepared. The title of the text is Wave, Sound, and Light. Now, let's understand what a wave is. A wave is a vibration that propagates from one point to another through a medium or vacuum. Waves transfer energy without permanently moving the particles of the medium. There is a formula to calculate the speed of a wave, which is v equals f times lambda, where v is the velocity or speed of the wave, f is the frequency, and lambda is wavelength. This formula help us understand how fast a wave moves depending on its frequency and wavelength. Now, let's talk about the types of waves. There are two main types, transversal and longitudinal waves. Transversal waves are waves in which the direction of vibration of the medium particle is perpendicular to the direction of the wave propagation. A good example is like waves or waves on a string. On the other hand, longitudinal waves are waves in which the vibration in direction is parallel or in the same direction as the wave moves. A common example of this is sound waves in air. So, the main difference between the two types lies in the direction of the vibration compared to the direction the wave travels. Next, let's move on to sound waves. So, sound is a type of longitudinal mechanical wave. That means it needs a medium to travel through, like air, water, or solid objects in a vacuum. Sound jets can travel. That's why space is completely silent. Now, sound has two main characteristics. First, how loud the sound is depends on its amplitude. The bigger the amplitude, the louder the sound. Second, the pitch of the sound, whether it's high or low, is determined by its frequency. The higher the frequency, the higher the pitch. For example, a whistle makes a really high-pitched sound because is it has a high frequency. Meanwhile, the deep thum-thum of a drum comes from low frequency sound. When calculating the speed of sound, the formula depends on the medium. In air, we usually use the basic one, but in liquids and solids, the formulas are a bit different. For solids, the formula is V equals the square root of E over rho, where E is Young's modulus and rho is the density. For liquid like water, the formula is V equals the square root of B over rho, where B is the bulk modulus and rho is the density of the liquid. So, basically, the denser and more elastic the medium is, the faster sound and travel through it. Now let's talk about sound wave phenomena. There are three explained: the Doppler effect, resonance, and sound gliding. First, the Doppler effect. Have you ever heard an ambulance siren getting louder and higher as it comes closer, then lower as it moves away? That's the Doppler effect. When the sound source moves toward you, the frequency sounds higher. When it moves away, the frequency sounds lower. Next, we have resonance. Resonance happens when an object starts vibrating because it's exposed to a wave with the same frequency. A good example is when you sing in the bathroom and hit the right note, your voice might suddenly sound louder. That's resonance. And lastly, sound gliding. Sound gliding is when the pitch of a sound changes smoothly over time, like when a singer slides from one note to another without stopping. In physics, this can also be connected to change in the energy of the sound wave. Unlike sound, light is an electromagnetic wave. That means it doesn't need a medium to travel. Even in a vacuum, like other space, light can still move. That's why sunlight can reach Earth. Light has several main properties such as first interference. This happens when two light waves overlap and create a new pattern. Depending on how they meet, the waves can strengthen or change or cancel each other out, forming bright and dark patterns. Second, diffraction. Diffraction is when light spread out after passing through a small gap or around an obstacle. This makes the light bend slightly and reach areas that you would expect. And finally, polarization. Polarization is when the vibration direction of light waves is limited so just one direction. Normally, light vibrates in many directions, but polarized light only vibrates in one. This is the principle behind polarizing sunglasses, which help reduce glare. Now, let's talk a bit about visible light and some optical phenomena. Visible light is the part of the electromagnetic spectrum that our eyes can detect. Its wavelength range from about 400 to 700 nanometers, from violet to red. It's the light we see every day, like sunlight, like bulbs, or our phone screens. Because of the light's behavior, like refraction, interference, and dispersion, we can see some amazing optical phenomena. For example, rainbows formed when sunlight is bent and split by raindrops in the atmosphere. Mirage, which happen when light bends through hot air and makes you see something like water that's not really there, or Sun halos, those glowing rings around the sun, caused by light passing through ice crystals in high clouds. So, thanks to visible light, we get to experience all these amazing natural visuals. Lastly, let's talk about the application of waves in daily life. Both sound and light waves play a big role in our everyday lives. For example, for sound waves, sonar, sonar and ultrasonics in medicine and industry, sonar is used in ships to detect objects under the sea. Meanwhile, ultrasonic waves are widely used in medicine, like in ultrasound scans, and in industry to detect cracks or defects in metal. The Doppler effect in traffic radar. This is used by the police or traffic officer to measure the speed of vehicles. It works based on the change in frequency of sound or electromagnetic waves reflected by moving objects. Next, we have light waves. Light also has many cool applications in our lives, such as microscopes and telescopes. Both use refraction and focusing of light to magnify things that are either super small or really far away. Display technologies like LCD and LED, the screens we see on phones, TVs, or laptops work by controlling light to create image and colors. These technologies rely a lot on our understanding of light and its properties. In conclusion, waves, sound, and light are physical phenomena that are essential to life. They're not only interesting to learn about, but they also have many real life applications that make our life easier and more advanced. From communication and medicine to everyday technology, waves play a big role in so many areas. Next, we, we will go into the quiz. The first question is: a wave propagates at a speed of 10 meters per second and a frequency of 2 Hz. Calculate its wavelength. Okay, from the question, we know that the speed is 10 meters per second and the frequency is 2 Hz. We're asked to find the wavelength or lambda. So we simply divide the speed by the frequency. 10 divided by 2 equals 5. So the wavelength is 5 meters. Here's another example. A sound wave has a wavelength of 0.5 meters and a frequency of 600 Hz. What is the speed of the wave? Okay, the wavelength is 0.5 meters and the frequency is 600 Hz. We're asked to find the speed. So we multiply the wavelength by the frequency. 0.5 times 600 equals 300. So the speed of the wave is 300 meters per second. That's all for my presentation. I hope the explanation helps you understand more about sound and light waves and how they apply to our daily life. Thank you so much for watching and see you in the next presentation.